So here we're going to talk about what happens when we're trying to add a second substituent to the ring. So we've already had the resonances of anisole and saw, and you drew some other ones to see what is more of an orthodirector or paradirector. And for the most part, electron withdrawing groups are deactivators, and they're going to have a preference for the meta. So their regiochemistry prefers meta. Electron donating groups are going to prefer the ortho and para, so very little meta. And they're activators, and that's the general trend. And if that's not what you put in your previous stuff, you want to go back and fix that. But the only exception to the rule is halogens. Halogens by resonance are going to direct ortho-para, but by induction, they're electron withdrawing groups and they deactivate the ring. So they make the ring slower, whereas electron donating groups make the ring more nucleophilic and more faster. And so here you see that I have some drawings of where I'm going to go with this. I'm going to actually redraw this for you. But there are two aspects to reactivity. So we've been talking about that pretty much all semester. If you're in my class that semester, we did as well. And if you don't remember, we did. And so when a reaction has two molecules collide, there is the ability for them to have a reaction, which is what happened when we were looking at the resonance structures that you just drew and looked at what places had more negative charge or what places lacked a positive charge. But then a reaction can't be just sustained by collisions. It has to be sustained by the ability for the intermediates to happen and getting us there. So what we're going to draw is when we have a substituent already on the ring, what are the sigma, or another word for that is rhenium complexes that form, and how does that predict how the reaction is going to continue in order to get to the final product. So we're going to start with benzaldehyde. And so benzaldehyde, we know, has an electron withdrawing group on there from the aldehyde. So it's an electron withdrawing group, which we know is a deactivator. And deactivators have a preference for the meta position. And so what we're going to look at is why once we see a collision happen at the meta position versus we're going to focus on the para position. So the ortho position behaves just like the para position, except there are two of them. So statistically, the orthos will sometimes happen more often, as long as the group on there is not too bulky to prevent it from happening at ortho position. So there can be a steric issue there. That's a different story altogether. But we're going to look at how are we sustaining that reaction. So remember, one of your learning objectives was looking at electronics. We're looking further at the electronics. So if I'm going to draw this reacting with a methyl cation, and I'm going to interact with the meta position, I'm going to draw all the resonances. So that's what you're going to see. And we'll be back in a second with all of these resonance structures drawn out for us. So you're going to see them out. And then I will actually give you a kind of concluding statement about what's supposed to happen when we draw it at the para. So you're going to see that you'll see that they'll all be drawn in just a second. So now we're going to draw what happens when it goes to the para position. And again, we'll do the same thing. We'll draw all the resonances out, and then we'll talk about what's going on that's different. And we'll do the same thing for an electron donator, and then we're going to compare. So what we see is that they both have the same number of resonances, but there's something peculiar about one of the resonances in the para position. And in this case, we see that there's a plus charge next to the carbonyl carbon. But remember that carbonyl carbon is partially positive, which means that we have a positive near a partial positive, and that's not stable. And because of that, that means this is a poor contributor. And so even though they both have 3, one only really has 3 really decent ones, and the other one only has 2 decent ones and 1 not so good. So as far as resonances go, this is not as good of a pathway. Now, it doesn't mean it doesn't happen, right? All of these typically will happen to some extent. Very few things can prevent some of the ratios of things not to happen, but majority of the product is going to be the meta. So let's go ahead and do one with NN dimethyl aniline, and we're going to do the same thing. We're going to react it with that methyl at the meta position. We're going to draw all the resonance for the sigma complexes, or arenium is the other word for that. And you're going to see by the power of recording magic, you'll see all of the answers on at one time for this one in just a second. All right, so this is the last one for the meta, and then we're going to draw the ones for the para. So I'm going to use my nucleophile to attack the methyl cation at the para position. And then we're going to draw the resonances. And then we're going to see what difference does that make. So remember, this is an electron donating group. Can donate into the ring. And so when I pick this up at the meta position, it's going to look like this. And then I'm going to rotate around the whole ring. And so if I keep drawing all the resonance structures, one of them includes a secondary resonance. And that secondary resonance looks like this. So that's that group that's outside of the aromatic ring, contributing to the resonance stabilization. And then there's one more resonance structure that can come from that middle resonance structure that would look like this. And so by drawing out these resonances, we see that we now have an additional resonance structure. We have 3 where it's rotated around the ring, plus we have that secondary resonance demonstrating that we're able to use those lone pairs to help stabilize and add an additional, so this pathway is more stable. And so that's another reason that it's going to have a preference for the ortho and the para. The para will give you very similar resonance structures. So I'm going to have you do one, and then you're going to practice with that one for the molecule that I gave you, and then you're going to move on to the next clip.